Hi, everyone, and welcome to our traditional Wednesday ITMP seminar. And today we are, uh, and today we have a talk from Maria Nocchi, University of Oxford, who will tell us about string amplitudes in antidecatur and what we can learn from the Regge limit. Maria?
Thank you so much. Thanks for the kind invitation and introduction. I'm very happy to be here today with you, and I will share some recent developments about this program of how to compute string amplitudes in AdS from different perspectives. And in the second part of the talk, I will try to focus on the last paper that we had a couple of months ago about the Regge limit of the amplitudes and what we can learn from this about the full amplitude. So the program of today is to give you an introduction and motivation behind this whole program of scattering of gravitons in AdS. And I will also take like a couple of minutes to comment on which kind of functions that we are going to work with. And I will introduce you to the program of AdS Virasoro-Shapiro amplitude. So we'll try to cover what's known up to now, what's our proposal, and what we have been learning until now. And as I was saying, in the second part of the talk, I will then get more precise and detailed about the Regge limit of this amplitude. So first of all, let me give you some motivation behind why we care about string amplitudes in AdS. If we forget about the context we are working with, we just think about scattering amplitudes. They are fundamental objects lying at the interface between particle physics, mathematics, and string theory, and they give us the probability for a certain process to happen. So it's a very strong predictive tool that simultaneously allows us to uncover structure and symmetries that could be not easily seen in the general theory. If we now move to a specific setup, the string theory setup, in flat space, we have a well-established setup, which is a perturbative string theory, and we have the worldsheet descriptions that allow us to write an endpoint amplitude in terms of the worldsheet integral. So we have two main parameters. GS is the string coupling constant, and usually in a perturbative setup, we think about sending GS to 0, and as I draw here. But we also have alpha prime, which I didn't write explicitly here, but it's a parameter of the Polyakov action of the theory and tells us about the size of the string. So we would expect that as we tune alpha prime, we will access different regimes of the theory. For example, alpha prime to 0, it's really shrinking the string to a point, so it's going to be the particle physics limit. So for example, supergravity in the case we're going to deal with. But we can also take alpha prime to infinity and investigate the opposite regime. I will comment on this in a few slides. Of course, the dream would be to solve this for alpha prime finite, so we'll also comment on how difficult it is to do this in flat space and in AdS. When we consider a scattering process, we sum over all the possible configuration of the worldsheets, this sum over topologies, that corresponds to taking Riemann surfaces of increasing genus. For today's talk, we'll just focus on the tree-level case, which is genus 0, and we can see what we can learn there. Just a small comment, in some regimes, this sum is dominated by a saddle point, and we can do exact computations, and we will try to exploit this also when we have a curved background. That said, an outstanding question is, what about curved spacetimes? And as we try to extend the standard formulations of string theory in flat space to curved backgrounds, to general curved backgrounds, modulo some specific cases, in principle, we have a perturbative genus expansion, but we have a lot of difficulties with extending the standard formulations. And above all, there is no direct worldsheet approach, even at tree level. That's why it is very important to learn new techniques to investigate these amplitudes. So the lesson to learn is that we need additional tools. In our favor, we have AdS CFT, that's going to be the main tool of today's talk, that tells us how to compute string scattering amplitudes on AdS from CFT correlators of the dual boundary theory, where we have a lot of tricks and techniques that we can use to learn about the bulk theory. So the strategy is to combine the worldsheet intuition that we have from flat space with alternative powerful tools, such that AdS CFT, as I was saying, but also number theory, integrability, and try to guess an answers for this kind of functions. Since this is going to be what I will focus on for today's talk, I will also comment briefly on why we care about high energy limits in general. So as I said at the very beginning of this talk, as you drive alpha prime to 0 to infinity, you access different regimes. For example, the high energy limit is defined as alpha prime going to infinity, which is the very stringy behavior of the theory. The high energy limit in flat space is defined as taking large S and T, where S and T are the usual Mandelstam-like variables related to the momentum, but we keep S over T fixed, which is the scattering angle. In QFT, we are used to thinking about the short distance behavior of the theory because it plays a crucial role, for example, in the OPE expansion, the RG flow. But the very first motivation behind studying a energy limit back to the 80s with Gross and Mende was, what about string theory? What can we learn about the short distance behavior of the theory? So we'll comment on this, but also I will comment on what universality is in this context. And then we will also understand why these regimes, when the energy is high, are good to make a direct contact with the string worldsheet, at least at the classical level. But what we were interested in doing was to explore a Ritter limit, which is the Regge limit. So now T is large, but S is finite. And this is Ritter because it encodes full information on the intermediate operators exchanged in the process under analysis. But also one of the very first novelty of Regge theory was that you can write down the answer in this limit without knowing the full amplitude, which is very constraining for us. But let me tell you about the main object of study. To test our proposal, we're going to focus on the paradigmatic example of scattering of 4 graviton states at 3 levels. In flat space, this is given by the Virasoro-Shapiro amplitude, which is one of the earliest results of string theory. So we are thinking about 3-level amplitude. The topology is a Riemann sphere with 4 punctures associated with the vertex operators that are our final and initial state. And this Z is the cross ratio of these 4 points on the sphere, while S and T are the Mandelstam variables that I was mentioning before. One thing that we can do is to use symmetries to isolate the prefactor depending on the polarization vectors, and then we are left with this integral, which is the worldsheet integral, and I'm going to refer to this as the reduced amplitude. That's what we're going to work with. An important observation is that the integrand is a single valued function of Z. So as you move around each puncture on the worldsheet, the function is single valued, so it's perfectly fine. It doesn't imply anything. But now we are interested in a curved background, and we move then to a D5 cross S5 that still, even in the presence of a maximally supersymmetric background, stringy corrections are very challenging to compute. And we don't know how to do perturbative string theory in this background. In particular, through the DSFT correspondence, this amplitude will be mapped to the correlator of 4 stress tensor multiplets to leading non-trivial order in a 1/C expansion, where C is the central charge of the CFT. I will be much more precise in the following. Arguably, Mellin space is the right language where to study holographic correlators because it is a setup where the correlator really looks much more like an amplitude, and it allows us to see more similarities and novelties with respect to the flat space amplitudes. So we're going to look at this, but in our program, we take an additional step, which is to go to Borel space. And Borel transform of the Mellin amplitude is our working definition of the DS Virasoro-Shapiro amplitude. So before going into details, let me just say that there are 2 main motivations behind this program. On one side, we think about the DS amplitude as a curvature expansion around flat space. So we want to understand how to analyze and include the curvature correction, which is in a way which is systematic and efficient. On the other side, we found that the way to do this is to exploit and make manifest the interplay between string theory and number theory. And speaking about number theory, I will take a few minutes, as I was saying, to comment on the special function that we're going to work with, just to refresh the main concept. For today's talk, we're going to consider this family of integrals related to some closed string theory amplitudes. And it's a worldsheet integral. It's just a generalization of, for example, the worldsheet integral that I showed before. S is a collection of Mandelstam kinematic invariants. They contain alpha prime. So in order to access the asymptotics of this kind of integrals, we will tune S. And then these n are just some integer numbers that you can tune to reproduce some amplitudes that you're interested in. For example, if you want to look at the Virasoro-Shapiro amplitude, turns out that you have to pick these specific values, but you can also reproduce different amplitudes, of course. An important point from number theory, due by Vanhoff and Zerbini, is that the global, meaning any S property of this kind of integrals, but also the local properties, are related to the theory of single-valued periods that are special functions such as zeta values and polylogs. And in particular, if you study the asymptotics of this kind of integrals, you find that the low energy expansion, where you take alpha prime to 0, contains only very special numbers that are known as single-valued multiple zeta values. So let's try to introduce the polylogs and the zeta values. Very briefly, we are used to the classical polylog, which is a convergent series on the unit disk. So it's this series above. What we can do is to improve the region of convergence of the function and continue it analytically to the cut plane by this iterated integral representation. So Li1 is proportional to a log of 1 minus z, and then by this iteration, we will build the higher n polylogs. A nice observation is that as you take z equal to 1, you reproduce the usual zeta values. So we will think of the zeta values as the polylog at unity. A possibility is also to allow the polylog to depend on more letters. So here it depends only on n, but you can also allow it to depend on a word. So we think of a word W made of letters in the alphabet 0 and 1. And this is going to just be a function of a single variable labeled by this word W, whose length we call weight. So the multiple polylog is the solution of these differential relations with the condition that for specific choices of the word, for example, for the word made by just 0, you reduce to powers of logs. And again, the multiple zeta values are just the multiple polylogs at 1. But even just from this integral representation, what we can notice is that since the log on the complex plane has a branch cut on the negative real axis, for example, this will predict that the polylogs will also have branch points and branch cuts, in particular for z greater than 1. So even if these functions are really nice to work with, they are discontinuous across the cut. One can compute the discontinuity and find that it is a logarithmic discontinuity. So for our purposes, the polylog is a special analytic function of a single complex variable with branch points, meaning that it is multi-valued on the complex plane. So the last step that we can do is to consider different combinations of polylogs such that all the branch cuts cancel, and we will define single-valued functions in the ZZ bar plane. Of course, you can do this also at the level of the multiple polylogs, and this will define for us the single-valued multiple polylogs. Again, it comes as no surprise that the single-valued multiple zeta value is just the single-valued multipolylog at unity. A very basic example to build this kind of functions, for example, for the log, is just to add the log of z bar, and that will give us like a single-valued version of the log. You can do way more intricate things, but for each polylog, you can build a single-valued version. For example, up to way 3, which is a polylog with 3 letters in the word, you can write each single-valued multipolylog just in terms of log and classical polylogs. And then there are a lot of algorithms by today in order to do different analytic continuations. And to conclude, I wanted to underline that at any given weight, meaning the number of letters in the word, there is only a finite dimensional vector space of available functions. This helped us because it's nice when you have an ansatz to have a basis of function which is finite dimensional, and that was also very nice to look at. So in our program of how to define amplitudes in AdS, reminding that we think of the AdS amplitude as a curvature expansion around flat space, our building blocks will be exactly these single-value multipolylogs, and I will try to motivate why this is so. So let's start from the Virasoro-Shapiro amplitude in flat space. This is a beautiful result given by this ratio of gamma functions. And this is the reduced amplitude, meaning that there should be an overall factor about the graviton polarizations, but we will focus on the reduced correlator, the reduced amplitude. There are some properties of this amplitude, and to be precise, when it was first computed, they didn't know about the worldsheet interpretation. They just guessed the answer by looking at the properties that they would expect it to satisfy. And these properties are that it is crossing symmetric in the three Mandelstam variables. And then we can look at the polar structure of the amplitude. For example, if you fix T and vary S, you will see the poles at the mass of the exchange state, so the tachyon and then higher states of the closed string. That happens because the string amplitude can be thought of as an infinite number of S-channel three-level QFT diagrams. Then you can start investigating different regimes, as I was also mentioning before, by tuning this alpha prime. For example, we can look at the Regge limit and the low and high energy limits. These are very well known. I will comment on them in what happens in AdS about these limits. In particular, I'll start from the low energy expansion of the Virasoro-Shapiro in flat space. We say that when we take alpha prime to 0, that's really the point particle limit. So it comes as no surprise that if you do this limit for the previous amplitude that I showed you, you get the supergravity limit, the supergravity answer. But then, as you include corrections in alpha prime, you will get this infinite tower of stringy corrections. And maybe less appreciated representation for this amplitude is this one. So you can show that the ratio of gamma function can be reproduced by this ratio of the exponential and the supergravity result. And I really like this representation because it's explicit the kind of numbers that appear. And indeed, if you look at this exponent, we have only zeta values at odd integers. And indeed, these are the single-valued multiple zeta values. These coefficients here in the stringy corrections are called Wilson coefficients. So we will remember in the following that in flat space, the low energy expansion of cross-string theory amplitudes contain only single-valued multiple zeta values. From a certain point of view, this reflects also the single nature of the single-valued nature of the integral representation. So we would like to understand better this single-valuedness, but at the moment it's just an evidence. It would be amazing to gain more intuition, physical intuition before that. It's going to also be just an assumption in our program, but it will be like it's a future direction how to properly understand this. So before introducing you to the program itself, let me make some takeaways. In flat space, we can use the worldsheet theory to compute string amplitudes. And importantly, as we take the low energy expansion, so alpha prime to 0, we have only very few special numbers appearing there, which are these single-valued multiple zeta values. The next step is try to use what we learned now to compute string amplitudes on curved backgrounds, where again, we lack a worldsheet technology in general. Okay, so I told you that the main tool is the SCFT correspondence. So we're gonna map the scattering of massless strings, in particular 4 gravitons on a DS5 cross S5, to a correlator or 4 stress tensor multiplets in Mellin space at large central charge. And the way the two sides of the correspondence talk to each other is summed up here. So on one side, we have alpha prime over r squared, where r is the radius of AdS, which is identified with 1 over square root of lambda, which is the 't Hooft coupling. And then also GS, which is the string coupling constant, as we take it to 0, which is the weakly coupled strings regime, this is mapped to large N on the other side. So we're interested in large N CFTs, which admit a weakly coupled holographic gravitational dual. What we propose is to do an additional step and to do a Borel transform of the Mellin amplitude. The Borel transform is implemented by this integral transform. And the key point is that once you do this integral transform and you take the small curvature correction limit of the Borel amplitude, you reproduce on the nose the ratio of gamma function that I showed you before. So the Borel amplitude of the Borel transform of the Mellin amplitude at leading order is exactly the Virasoro-Shapiro amplitude in flat space. And then we keep the infinite tower of curvature corrections as working definitions of our AdS corrections. I just want to make 2 comments about this slide. The first is to be a bit more precise about the CFT point of view, for those of you who are interested. From a pure CFT point of view, we are studying the 4-point correlator in n equals 4 super N mills at leading non-trivial order in the large central charge expansion. So we have this 4-point function where O is the superconformal primary operator of the stress tensor multiplet. It's a scalar operator. It has protected dimension 2, and it transforms in the symmetric traceless representation of rank 2 of the SO6 R symmetry group. Then, as usual, we can use the superconformal word identities to extract the R symmetry prefactor, very much more like what we did in flat space with the polarizations of the gravitons. And then this is really the object that we are computing in the CFT, a reduced correlator that will define for us the reduced AdS Virasoro-Shapiro amplitude in the bulk. But also, even if it's not perfectly understood why this is working, I would like to make some comments that may lead to some discussion about why Borel space. I told you that this is just an integral transform given by this expression, and there are different intuitions behind why we use this. A first comment could be a technical comment. If you do the Mellin amplitude of 4 gravitons and you take the low energy expansion in Mellin space, it's not summable because the radius of convergence is 0, given by the presence of some gamma function, but it is Borel summable because Borel transform essentially eliminates the gamma function. So in order to make contact with the string worldsheet, we do need to understand how to resum the low energy expansion. That's why Borel space turned out to be very interesting in this sense. But also, this transformation is nothing too exotic. At leading order in 1 over R, this is just implementing the flat space limit introduced by Penedones in Mellin space, where S and T are interpreted as the Mandelstam variables in flat space. Our proposal is to also keep the 1 over R corrections to this flat space limit and take them as working definition of the DS corrections. So from now on, we will always work in Borel space. Whenever we talk about the amplitude, I mean the Borel amplitude. To sum up, we are in a DS CFT. We want to investigate the analytic structure of the DS amplitude. And this, from the CFT point of view, corresponds to understanding the intermediate operators in planar n equals 4 super N mills. This is a prime target of integrability, so it's also nice to understanding how to talk with the integrability community through these computations. The conjecture is that single valuedness is a driving principle to analyze the DS amplitudes exactly as it was in flat space. And by taking single valuedness and adding it to the list of properties of the Virasoro-Shapiro amplitude in flat space, we saw that it was possible to see this emergent worldsheet picture. That's the key point of this program. And there are 3 key points, three key points behind the proposed amplitude. The first point is that in flat space, the Virasoro-Shapiro amplitude has infinitely many poles, but they're all single order poles. But if you take the curvature corrections, you can see that the DS corrections have higher order poles that jump by 3. There are various ways to see this. One way could be to take the bulk-to-bulk propagator and expand it and see that it does have higher order poles. The second key point is about the low energy expansion. The main assumption here is that the unknown coefficients in the low energy expansion of the DS corrections are single valued zetas, exactly as in flat space. The third point, as I told you at the beginning, we are combining different intuitions, but the main one is the one from the worldsheet. So we're going to assume that the worldsheet integral is exactly as in flat space, with insertions of single valued functions, such that this is satisfied. And if we want the low energy expansion to contain only single valued multiple zeta values, it turned out that there are very specific functions that can reduce to that upon integration of the Riemann sphere. And these functions are the single valued multiple polylogs. So this is the proposal for the structure of the three-level amplitude on AdS5 crosses 5. There is this curvature expansion, and each correction is in terms of weight 3K single-value multipolylogs and rational functions of S and T. The jump by 3 respects the jump by 3 in the polar structures that I mentioned above. And again, this is not at all the result of a direct worldsheet computation, but it came from combining different tools with the intuition from flat space. We learned that single values seems to play a fundamental role in the construction of AdS scattering amplitudes as in flat space, even if we really would like to understand this point better. And as a strong support for this proposal, Fernando and collaborators were able to compute exactly some CFT data and compare with all the known integrability and localization results from planar and equals for supergaminous strong coupling and found perfect matching. Also, I forgot to say this, but this is made in collaboration with Luis Fernando Alday and Tobias Hansen, Clement Virali, and Shinanzu. So we'll mainly focus on the papers about high energy limits, but what I say up to now, it really comes from the whole papers that we had in the past 2 years. And the big goal of this program would be to determine the AdS Virasoro-Shapiro amplitude to all orders in 1/r. But in the meanwhile, we are trying to focus on more accessible limits, in particular to make connections to more direct worldsheet computations, and to explore the structure of the proposal by probing the theory in different regimes. We investigated the energy limit, and I'm gonna briefly recap what we learned about that. And we thought that the next step would be to investigate the Regge limit, which seems to be a much richer limit where to look at, while still being able to do exact computations. So if there are no questions up to now, we'll start with the high energy limits of the Virasoro-Shapiro amplitude and what we can learn about the full amplitude now.
Could you please repeat once again, like about single valuedness? So is it a property, so it's about dependence on Z, which is like on the worldsheet? And how does it translate eventually to dependence on Mandelstam variables? So how does it constrain your ansatz for amplitudes?
Yes. So single valueness is just about Z. So if you are on the worldsheet, whatever that is, you're saying that as you go around any puncture, the functions appearing there are single valued. And then I think the only constraint on S and T comes from the region of convergence of these kind of integrals, which is like the real part of S and T is negative, and there is some constraint on their sum. So that's all we have here. I don't think there is more about the dependence on S and T, apart from the fact that they only appear as rational functions. So each curvature correction is a weight 3K, single value combinations of single value multipolylogs, and it's a rational function in S and T.
Sorry for interrupting, Maria. I just want to reiterate. I have a very silly question. So, where do we see the difference from the flat limit, and how does it manifest? And what if, for example, we were curious about doing calculating the same amplitude over, I don't know, other homogeneous space, maybe over the theta or over, I don't know.
Right.
So what is so how does this being on a curved manifold manifest itself?
How does the background you're working with? Okay. So first we are working with AdS because we have AdS CFT. So our tools are mainly number theory and CFT techniques. So from the very beginning, if you have like the theta, it would be much more complicated to use these strong constraints from CFT. If we focus on AdS and you have a different background than AdS5 crosses 5, you can also make an ansatz very similar to this, because at the moment, I think this is your question. You don't see any dependence on the specific background. For example, you do know the jump by 3 by the specific propagator on AdS5 crosses 5. But for example, Fernando and collaborators had this paper on AdS3 crosses 3, where they use exactly the same ansatz, and it seemed to work fine. In that case, you have more control. So I would say that up to here is pretty much general once you are in AdS. And it would be great to understand also like how to see the appearance of AdS itself, but also the compact manifold that you have in the SFT. This is not clear, I think. But as you were saying, I think this is pretty general. So you could try to do these ansatz for any background in AdS and see how to constrain the coefficients. An important point is that, for example, for AdS5 cross S5, we were able to fix entirely the first two corrections because we know from integrability the dimension of Konishi operator in an equals for supernormal means at strong coupling. So I think that you do need to know some CFT data from the boundary theory. If you don't do that, maybe you could still write an ansatz, but the coefficients will have to be fixed with more information, I think. Does it make sense?
It does.
Okay.
Thanks.
Thank you.
Yeah.
Okay.
Could you please also comment on this Borel transform?
Yeah.
So it looks like it pretty much just undoes the Mellin transform, right? So it looks like, no, it's not Mellin, it has exponent, right?
Yes, exactly.
And where does 5 come from?
From an equals for supernomials. So that will change when you will change the theory. Mm-hmm. It's related to like the R symmetry and the quantum numbers that you have in this theory. But the Borel transform is just like e to the minus beta, and you do some shifts of the arguments.
Okay. And is it true that the Mellin amplitude just has simple poles? So
yes.
You said that, and A has like what's called multiple.
Higher order. Okay. Yes, as you expand, yes, exactly.
Mm-hmm. Okay, thank you.
Thank you. Okay. Thanks for the questions. Okay, let me recap briefly what we learned from the high energy limit to then go to a richer limit. So high energy means that we are taking S and T to be large with S over T fixed, exactly as in flat space. And we have the two different perspectives to look at this limit. On one side, we have the space-time point of view. From the very nice work by Gross and Mende back to the 80s, we know that in flat space, the path integral is dominated by a single-valued classical solution, which is the one that I wrote here. And in AdS, we did exactly the same analysis, proposing a bosonic model for the scattering of classical strings, and we solved for the equation of motion in 1 over r. Again, what we found is that at each order in this curvature expansion, the functions appearing are single-value multipolylogs, and they are these L1, L3, L5. So we have jumped by 2 in the solutions of the equation of motions, and some combinations of transcendentality 3K each term. But we have another perspective, which is the worldsheet point of view. In flat space, you can look at the worldsheet point of view and see that you can solve for the integral in this limit by saddle point approximation. And that's the saddle that you have. So you just use this approximation and you get the famous soft exponential behavior of high energy limit in string theory, which is so drastically different from like QFT. The next point about AdS here is that, as I was telling you, our proposal for the answer is that we have insertions in the worldsheet, we have insertions of weight 3K single value multipolylogs, but these insertions are just rational functions of S and T. So it means that they cannot modify the location of the saddle point in a 1 over r expansion. So the answer in AdS would just be to evaluate the ansatz that we have on the saddle point from flat space. If we then require that the 2 point of views match, we found this beautiful formula, which tells us that the energy limit of the AdS amplitude is the flat space limit in the high energy limit times this exponential that gives us the whole information about the curvature corrections, where W3 is the first correction in the integrand, in the worldsheet integral, evaluated on the saddle point from flat space. So in this regime, we can compute the amplitude to all orders to be more precise in S over R fixed and curvature corrections exponentiate, which is an exact result, and people have been using these to constrain the curvature corrections in other backgrounds, such as as well as to verify that the answer was correct. So the question is, can we explore a Ritter limit? Luckily, we could, and this is the Regge limit that I'm going to talk about now. So first of all, some motivation behind why Regge limit. It's a Ritter limit, but from a physics point of view, let's try to understand why it is interesting. Historically, Regge theory turned out to be very useful in the presence of infinitely many resonances in scattering amplitudes. That was the case for QCD and for string theory. And once we knew about the SFT correspondence, it was natural and interesting to try to generalize the Regge theory to scattering in AdS. That was the conformal Regge theory paper by Costa, Gonçalves, and Penedones. So we're going to take this spirit in our project to look at AdS Virasoro-Shapiro in this limit. Let's focus on the main object of study, which is the Virasoro-Shapiro amplitude in flat space. We saw that we have this ratio of gamma functions, so we have infinitely many poles for the exchange particles, and these particles organize in Regge trajectories that I plot here. So these trajectories are linear, and there is this delta, which is 1, 2, 3, and so on, and that's called flat space string mass level. The big achievement of Regge theory is that you can get the amplitude in the limit without knowing the full result. The only two pieces of information that you need to get the result is the spectrum of the particles in the leading trajectory, this one up, and the cubic couplings. In our context, this means knowing the CFT data of Konishi-like operators that are target of integrability. So it was super interesting, honestly, to look at Regge limit and to learn about how integrability interacts with bootstrap techniques. What do we expect from AdS starting from the flat space limit? Flat space Regge limit is defined by taking large T and S finite, and the main thing to know is that the exchange of a single spin J state makes the amplitude scaling as T to the J. So in our convention, the Regge limit of the Virasoro-Shapiro amplitude in flat space is the following. We have some function of S, and then T to the J that I brought us to S minus 2 because we are interested just in the leading Regge behavior. So these particles live on to delta minus 1. So on the pole, it will be to S minus 1. AdS corrections now. I told you that we have higher and higher order poles as we go away from flat space. So we expect that these will introduce logarithmic corrections to the flat space answer of the form log T to some power, where the power of the log is fixed by the order of the poles. That's a well-known result in scattering amplitudes. So if you have an amplitude which has higher order poles, you would expect the Regge limit to go as T to the J times logarithmic corrections in T. Okay, so we have to do now two observations. First, what we would have in Mellin space if we wanted to implement the Regge limit, and then we want to use the ideas of Regge theory in Borel space. Very generally, if you want to write down the Mellin amplitude for the exchange of an operator of spin J and twist tau, we have this kind of formula. As we said just a few minutes ago, it has simple poles, and it is much easier to deal with, much more easy than the position space result. So we have a singular part as a sum over M, where M labels the descendants of the exchange operators. And then we will also have in general regular terms, but we will forget about this in the following, because in the Regge limit, they go at most as T to the J minus 1, while we want to study just the leading Regge limit, which is T to the J. In the AdS, we also have this relation that relates tau, J, M, and R, bulk theory and boundary theory. The residues of these simple poles in the Mellin amplitude are called polynomials, and they are particularly simple in the leading large T behavior. They indeed just go as T to the J. So this will translate to the Mellin amplitude in the Regge limit to go as a function of S times T to the J. So now we would have two options. one option would be to just compute the exchange amplitude explicit in the limit, or to look for a difference equation it satisfies. And usually in the Bootstrap community, we always choose the difference equation because we can expand, do manipulations, and we usually learn a lot from that. So we're going to take this approach and combine it with the idea of applying the standard Regge theory to the Borel transformed amplitude, where we can do computations. So let's translate what I just said about like the scaling of the amplitude in the Regge limit to the Borel space. And the first step in Regge theory is to analytically continue the partial waves in the amplitude as a function of the spin J. So first point, we have exactly the same behavior in the Regge limit for the Borel space, and we can write it in this form to make manifest the dependence on the partial waves. So in this context, in a CFT context, C squared J is the square of the OP coefficients of the external states and the exchange one. Then we will call these partial waves. And the behavior in the Regge limit is, as before, T to the J, where capital T is that Borel variable. So it's going to be the Borel-Mandelstam variable for us. The second step in Regge theory is to actually compute this contour integral. So this is the right choice for a contour integral to reproduce this sum over the spin. For example, this integrand is chosen to reproduce the poles at j equals 0, 2 that the amplitude has. Since we are working with Virasoro-Shapiro amplitude, I'll just take the poles at integer of even values of j. And the usual, very briefly, the usual strategy here is to deform the contour that we have here to go to this contour, which is parallel to the imaginary axis. And by doing this, you will pick up all the Regge poles that I wrote here as this single x, but you have the whole Regge poles. And since we are really interested just in the large T limit, the pole with the largest real value of j will dominate this integral. And this corresponds to the leading Regge trajectory, which are the operators of lowest dimension for each spin. This can be seen in detail. That's very well known. I just wanted to refresh the strategy to now do this for our case. So again, we learned that in a 1/r expansion, A contains poles of higher and higher orders at J star. What is J star? The location of these poles and the residues of these poles are determined by the difference equation satisfied by the Borel amplitude. So I'm not going to go into detail of this, but as I was mentioning, if you have a Mellin amplitude, you can always find the difference equation that it's satisfied. And then you do the Borel transform of this difference equation, you expand in 1/r, and you find the location and residue of the poles in terms of m squared. So in particular, J star, the location of the pole, is the implicit solution of this equation. Mj star squared is for S. And in the J plane, the complex J plane, this as a 0 in J star. So for convenience, we will factorize J minus J star and absorb what's left in this bit of J. But this is really just a manipulation. We are thinking about the location of the pole in a 1/r expansion. Then we use Cauchy's theorem as usual. And for each pole of order k here, we can write this contribution as derivatives. So this part here, we have a derivative with respect to j times a factorial factor. And we have this r, which are the residues of this pole, unknown at this point, and the bit of j that I introduced here. This is nothing really important, but what I want to underline is that if we now define the operator del j 1/beta j, and we call this y, then we are in the position to write a general solution for the Virasoro-Shapiro amplitude in the Regge limit in AdS in terms of this very compact answer. I told you that the key achievement of the Regge theory was to determine the amplitude just knowing the CFT data of the leading Regge trajectory. This is exactly what we found for AdS. And indeed, what we have here, we have an operator, curly R of y, where y, you can think of it as derivatives with respect to j. And this is the effect of the curvature of the background. because it is somehow the integral transform of the AdS amplitude. Then this is just from the Cauchy integral. But the important point is that the only ingredients that we need on the right-hand side are the CFT data, so the OPE coefficient and the dimension of the operators in the leading Regge trajectory, that in this case are the Konishi-like operators from an =4 super-Mills at strong coupling. So we found an explicit expression for the Virasoro-Shapiro amplitude in the Regge limit in terms of the CFT data of the Konishi-like operators only, which is very similar to what happens in flat space. At all order in 1/r, what you can do is to expand this R of y in a 1/r expansion, and we can do it at any order, and build the solution in AdS as derivatives of the flat space result in the limit. Because at the end of the day, this is just polynomials of S times derivatives with respect to J. And when derivatives with respect to J act on T to the J, they will eventually produce the log of T that I was mentioning before. So we do get logarithmic corrections in T as we go away from flat space. We can also infer some result to all orders in 1/r from this formula that we proposed. First of all, we can resum all the leading logs. For example, the first correction around AdS has at most a log cubed of T, then a log 6, log 9, and so on. We can resum all of them and see that leading logs exponentiate very nicely. And we can see that this is in perfect agreement with what we found from the high energy perspective in the right regime. So we have again this combination, we are looking at a specific regime. But we can do more. We can also resum the subleading logs. This was a bit more intricate, but we do find a closed formula. So this is an all order result in the limit of large R, large T, with log cube T over R squared fixed. So what I said in the previous slide is true exactly. This is an exponentiation that we can see in this precise limit, which tells us that we are close to flat space, but it would be also amazing to learn more about what happens when we go very away from flat space. And in the remaining 10 minutes, 15 minutes, I wanted to comment on what now we can learn about the worldsheet from the previous analysis, and also what we can learn about the full amplitude, so from Regge to the full amplitude of S and T finite. Okay, so AST, the AdS amplitude, is given by this worldsheet integral. It's the flat space worldsheet integral with the insertion of some function, which is single valued, as a rational in S and T. This is a combination of these special numbers and functions that I showed you. But even forgetting about that, if we want to engineer the Regge limit at the level of the integrand, the relevant limit is the one where you send T to infinity, but Z to 0 by keeping TZ fixed. So if you want to do the Regge limit at the level of the integrand, you just take this amplitude and you plug G hat instead of G. Some observations. At each order in 1/r, this G hat is a polynomial in Z, Z bar, and log of modulus of Z. This is the exact result, even because if you want to be more like from a mathematical point of view, this G contains single value multipolylogs, and you can show that as you expand the single value multipolylogs around Z equals 0, you will have a power expansion of Z, Z bar, and log of modulus of Z. So that's nothing too surprising. If we apply this to the Virasoro-Shapiro amplitude to order 1/r to the 4, which is what we have up to now, this agrees perfectly with the prediction from the other side of the computation, from like the derivatives acting on the flat space Regge limit. I need to tell you that there are ambiguities in this computation, and it happens whenever you have integrands to work with. So we are working at the level of the integrand, so you can always wonder whether it's defined up to terms that integrate to 0. And this is of course true, but there is a way to partially fix these ambiguities. For example, if we assume that the integrand remains finite as we take epsilon to 0, we found that this is true for the first two corrections in AdS, provided that the ambiguities are chosen appropriately. And there is a unique solution to this. I will comment a bit on the ambiguities at the end if I have time, but for a certain choice of the ambiguities, we can take the Regge limit at the level of the integrand. And that was nice and helped a lot in implementing these computations. We can also take the opposite point of view. So what we did here is to start from the integrand and implement the right Regge limit to reproduce what's known from the other side of the computation. But now we reverse the logic. And we start from the Regge limit that we compute from the other side now, and we want to get the right integrand, forgetting about single-value multipolylogs, and see what we can learn from here, and if this is confirm our proposed in terms of these special functions. We want to reproduce something which is derivatives with respect to J of the flat space Regge result. And if you look at this kind of integrals, you immediately see that if you insert a function which admits a power expansion in terms of log of modulus of Z, that will do exactly what we want and produce an operator which has derivatives with respect to J. This is the case because if here you insert log of modulus of Z, this is exactly the same as taking the derivative of the first term with respect to J, which is super nice. So we have whatever function this is, we just assume that this is a function of log of modulus of Z to reproduce the right derivatives. This is going to be the answer at the level of the worldsheet. But this has to match with this thing that we found from doing this difference equation in Borel space. So this is a functional equation for the right insertion in the integrand, the worldsheet integral, that can be solved to any order in 1 over R, because our R operator is known to any order. It's just the solution of this difference equation in 1 over R. Which is super nice, because now you can solve for this and find families of solutions for the worldsheet integral that lead to the correct Regge behavior to all orders in the curvature expansions, up to these ambiguities that anyway integrate to 0 in the limit. And let's notice this key point, that the right insertion is a function of a single valued log. And I told you that this is the asymptotic of single value multipolylogs. So at least we know that the integrand has to be manifestly single valued around Z equals 0, even from this perspective. So the key takeaways here are that the AdS Virasoro-Shapiro amplitude in the Regge limit can be written as derivatives of the flat space result, but also admits an integral representation with single valued logs. And once again, our proposal for the full amplitude is that the curvature corrections can be written as genus 0 integrals with insertions of transcendental single valued functions of weight 3k. And it seems that this is really a nice, nice evidence for our full amplitude. So I will try to sum up the key points of this program, and then I will comment the next couple of minutes about future direction and what we've been working on this couple of months. So this is really a program about how to compute string amplitudes and AdS, relying on the DSTT correspondence, integrability, and worldsheet intuition, using the strong tools from number theory. What it seems to be happening is that single valuedness is very important to understand and construct scattering amplitudes in AdS, as it was for some closed string theory amplitudes in flat space. So this led to a proposal of the AdS Virasoro-Shapiro amplitude as a worldsheet integral. It seemed then that the further step towards the worldsheet theory were to investigate these high energy limits to probe our theory in these regimes. And as I tried to motivate, this was the right place where to look for a more direct comparison to a putative worldsheet description of strings on AdS 5 crosses 5. What we learned is, on one side, from the high energy limit, that in this limit curvature corrections exponentiate, and we also have the leading behavior is captured by a bosonic model for classical strings on AdS, which is universal. So it is independent on the quantum numbers of the external states, exactly as in flat space. And for the new, more richer Regge limit, we also found that leading logs exponentiate when we look around flat space. And it was also very nice to get contact with integrability communities through these short operators in n equals 4 super Mills strong couplings that are the only piece of information that you really need to determine the Virasoro-Shapiro amplitude, even when you are in AdS, in a perturbative setup, of course. And I want to make evident, and once more, that from Regge limit, we learned that single valuedness of the integrand around z equals 0 is manifest much more than in the full ansatz. So the natural follow-up now would be to understand what if we assume single valuedness at 1. So like we start from a general answer, the Regge limit answer, which is manifestly single valued around 0. But what if we add z equals 1, which is the other important point to worldsheet? Are we able to reproduce the full amplitude? And that, I don't know, we have to investigate it. But as we already mentioned before, it would be also amazing to understand like what happens with other backgrounds. This has been done partially recently in the past month. For example, in AdS3, it was super cool because in AdS3 you also have like an exact worldsheet. So you can also compare with that, and it's very interesting. And the last 2 points are, what about these ambiguities? And since I have a couple of minutes, I will be more precise. When they wrote this proposal for the integrand of the Virasoro-Shapiro amplitude in AdS, these had some ambiguities, which are just terms that you can add to the integrand that integrate to 0. So we don't really understand this from a string theory perspective. I'm not an expert of string theory at all, but it would be nice to see if this is expected to happen from a string theory point of view, what they really mean. We fixed most of them from imposing that you can take the Regge limit at the level of the integrand, but I think there is more, so it would be nice to have a better understanding of that. And the last point is, now that we have these ansatz for the curvature corrections, what are the properties of these after integration? So just last week, we managed to integrate these curvature corrections and get the amplitude as an explicit function of SNT. It's very intricate, but now we want to understand what are the symmetries of the amplitude, what we can learn in terms of this Borel transform, and there is still a lot to do, which is great, while keeping in mind that the final goal is to get the answer to all orders in 1/R. And I think I'll stop here, and thank you for your attention.
Thank you for your talk, Maria.
Thanks.
Okay, questions?
I have a kind of side question. So in flat space, in principle, you can compute, say, one loop string correction, which is like a 1 squared correction on gauge side. So would you expect some of these features which you observed to be true as well?
Yeah, we haven't worked on that yet. I think, so there is one thing, which is how to get AdS higher genius amplitude by cutting them in 3-level amplitude. So that would be a way. But also I think even from number theory, it would be really possible to have an ansatz, but with different functions. For example, modular functions and elliptic functions, this stuff. I haven't worked with them, but it should be possible, yeah.
Okay. Yeah, that would be very interesting to see what.
Yeah, that's on the to-do list. I think it would be very interesting. Thanks.
Okay, my question can be a bit naive. So, well, I understand that high energy and Regge limit at different limits, but still, what happens if you set if you set T goes to infinity, so that if you set S goes to infinity, so that you recover high limit? Can you get some? Well, can you at least partially recover the high energy limit from Regge limit? That's what I'm asking.
So in flat space, yes. In AdS, no, because you are taking 2 different limits simultaneously, right? You're taking SNT large, or one of them, but you're also taking the radius to be large. So you have to be careful. But what we can do is if you take just the leading logs resummation in Regge limit, and from that you can see the same exponentiation in high energy by taking the large ST limit, and you just keep the leading logs. Because when you go to subleading order, they will be mixed with large R, large S, and there is a difference. You cannot recover the full high energy limit from the Regge limit. And one other comment that I should have said is that when we do high energy, what we really mean is we do large S and T, but with S over R fixed. So it's not the real high energy limit in AdS. It's the Regge limit in a perturbative setup when you're really close to flat space, but we still have to develop technology to include more the curvature corrections. While in Regge limit, from one side, we have the exact Regge limit, and then you can do the resummation just in a setup that is compatible with Regge with high energy. But you cannot recover the full answer, as you were saying. Because the Regge limit exponentiates only when you keep this log cube t over r squared fixed. So it's a specific limit where you see this exponentiation. Otherwise, you still have an explicit answer, but it's not just an exponential. So this, here this exponentiation is seen in the limit where you are away from flat space, but not so much. T is large, but this ratio is fixed. And this is the same spirit as when high energy you do S squared over R squared fixed. So yeah, it's still work in progress how to understand how to include more curvature corrections, especially in the high energy setup.
I see. Thanks. So I have another question, but I'll let others speak first. So if you have a question, please come up.
Well, I wanted to ask one thing. So if you sum up everything which is known at the leading order in the 1 over n on the CFT side, and everything that you know about AdS, so like I don't know who made more progress, or can you learn anything new about CFTs from what you did in AdS? Because to the best of my understanding, in the Regge limit, essentially your results are just the CFT results, right? You just rearrange them into an amplitude.
Yeah.
And this, I guess this is conjecture about single valuedness. I guess it brings some new information. What does it mean on the CFT side? Is it known?
Yeah, so for example, you can determine the OP coefficient for the CFT. The integrability cannot compute because they determine the anomalous dimensions. But from our side, so you can determine new CFT data for the dual CFT by just looking at the polar structure, right? That will tell you about where the poles are. So these anomalous dimensions, but also the residues that contains the OP coefficients. And yeah, it is true that it is rearranging the CFT data, but this R of Y contains the effect of the curvature. So in 1 over R, term by term, you will get the correction around flat space of the whole CFT data that you have on the other side. I don't know if this is what you were asking for.
Yeah, and concerning, you said that there are some new relations on the CFT side, and the CFT people don't know how to explain them.
You mean like this?
Well, I don't know exactly what you meant. You said that there are some kind of results that you produce. They give some new relations on the CFT data, apparently which was not known before, right?
Yes, so this is not in the Regge limit. This is exactly with S&T finite. Because once you compute the two curvature correction around flat space, then you can extract the residues of the poles, and that will map to the OP coefficients of the CFT data, and these are new. So Fernando and collaborators did this for the first two corrections around flat space, up to 1 to the R to the 4. Then I guess you can do this also in the limit, but you can really do this exactly when S&T are finite. And in principle, from a purely CFT point of view, our determination should be the Borel transform of what they did in the conformal Regge theory paper a while ago that was done in Mellin space. If you look at that paper, it's way more like CFT, and there is the precise determination of these things that I was mentioning. But the nice thing here was how to get implications on the worldsheet from the CFT point of view.
Mm-hmm. Okay, can you please also repeat? You said that the Mellin amplitude is not applicable because there is some summation that diverges. What kind
yeah, I think I have it somewhere. Let me check. Okay, yeah. So this is, for example, the Mellin amplitude for gravitons. And this cross S5 in a alpha prime to 0 expansion. Alpha prime is not written here, but the first term is supergravity, and then you have the tower of stringy corrections. And if you try to do this sum, the radius of convergence is 0 because of the gamma function. And this is very not precise, but if you take the Borel transform of this, what Borel transform does is to eliminate the gamma function and makes the radius of convergence finite. So this sum is Borel summable. You would need to do this anyway if you wanted to resum the low energy expansion to make contact with the worldsheet. That was just one technical point about Borel. But for sure, there could be other integral transforms. Borel seems to be nice, but could do other things to make this summable.
Mm-hmm. Okay, thank you.
Thank you.
Okay. So I have just a quite a general question. So since we're doing AdS-CFT some degree, how is it connected to calculating, let's say, Witten amplitudes?
Calculate what?
Witten amplitudes.
Witten diagrams?
Yeah, Witten diagrams, sorry.
Yeah, okay. So Witten diagrams are in position space. So if you were able to do that, then you could just go back from Borel to Mellin to position space. It's really just a change of integral transforms. Just in principle, then it's very difficult to do these contour integrals. But if you're careful, at the very end, you will also get the position space result. We're just picking a space where doing computation is easier. But yeah, indeed, it's the same. Like you could write down the Witten diagrams. Like these two expression here come exactly from Witten diagrams. So this is supergravity amplitude, and then this is the Witten diagram, contact Witten diagram for the stringy corrections. So you could do that. Then you have to bootstrap to guess the precise coefficients, and this depends on the answer, on the theory. Sorry.
Okay, I see. Thanks.
Thanks.
Okay. This is your last chance to ask questions. And we're going once. Oh, Arkady?
Yeah, I just wonder if, suppose we can try to reverse the history and you have no idea about CFT, you just look at the idea, you just know, say, superstring amplitude in flat space, and you try to generalize it to AdS. Then what kind of intuition you will use? So what is the data which you will use? I guess, suppose you know indeed this special properties of the coefficients which you want to preserve, but somehow you don't really know where to start with, right? Or
yeah, I think that's exactly true. Like it's the same spirit as like what Virasoro did in flat space.
Yeah,
like they didn't
you need to
right?
make a guess. Yeah,
so it's a guess.
Well, slightly better than Virasoro, then you can make a guess that it should be the two-dimensional integral of something, and then then you can write down some integral which mimics the flat space.
But you do need to know like the crossing symmetry, like that is fundamental.
Yes, and I guess all right. Thank you.
Thanks.
There is a question in the chat. Maybe I don't know.
Oh, okay. Can I see it somewhere?
Yes, is there a relation between AdS and CFT with the equations used in presentation? Okay, I don't, that's a bit confusing.
Sorry, I don't know where to look at the chat. Is the relation between the SMT with the equations used in our presentation? Yes, and CFT with the equation. If they can write it again, I don't think I got the question.
Yes, I'm a bit confused as well.
Yeah. The relation between the AdS and CFT with the equations used in our presentation.
Yeah, I guess we can skip this.
Yeah, they're very welcome to write me an email if they want.
Yes, we were a bit confused. So, okay. Well, now it's really your last option to ask a question. And we're going once, going twice. Okay, sold. Thank
Great.
you, Maria. We were most
Thank
delighted to have you here. And good luck with your post-PhD, with your postdoc life. So,
yeah.
Hopefully we will see you. Yeah, we'll definitely see you here again.
Thanks a lot.
Yeah, next year. Okay, bye.
Okay, take care. Bye-bye. Thank you.